In this video, I want to derive the continuity equation in fluid mechanics for fluid flow. Continuity means continuous. What is continuous here is the fluid itself, right? So you have fluid can be transported from one location in space to another. Its density can change, but it has to do it continuously. So how do we derive, why are we doing this in this lecture now? We're doing it because it uses the divergence theorem. It's a nice theoretical application of the divergence theorem. So to derive the continuity equation for a fluid, we need two quantities. One is rho, which is a function of position in the fluid and time. Corresponds to the fluid density. The mass per unit volume. The other is u, which is a vector field, which is a function of position and time, and that corresponds to the fluid velocity, right? The length per unit time. Okay, to derive a continuity equation, you consider a test volume. It can be any shape, any size. So this is called a test volume. And it's enclosed by a surface. So it's a test volume V, enclosed by surface S. Okay? And then let's try and write then how the mass of the fluid in this test volume changes in time. So we're writing an equation for the dm dt, the derivative of the mass inside this test volume as a derivative with respect to time. The mass of fluid in this test volume changes because of the mass flux through the surface. So I introduced the mass flux before. So it changes, it will decrease when the mass moves through the surface. The flux of the fluid mass through the surface is given by a surface integral through the surface. And then we have rho times u dot ds. So the units of this right-hand side is mass per unit time. The left-hand side is mass per unit time. And the mass, the time derivative of the mass in this test volume is equal to negative of the mass flux through the surface. Okay? So this is essentially the continuity equation. We want to put it in a more standard form. A more standard form would use m. So the mass in this volume is a volume integral over the density dv, right? The mass per unit volume integrated over the volume. That's the left-hand side. So then if we want to write dm dt, that's the time derivative of this. Rho is a function of position and time, but the volume integral is the integral that you're integrating over is independent of time. So we can bring the time inside of the integral. So that would be the integral over the volume, and we'll need to use a partial derivative here because rho is a function both of position and time, dv. Okay? So that will be the left-hand side. The right-hand side will use the divergence theorem. So we have the integral over the surface of rho u dot ds. Applying the divergence theorem becomes an integral over the volume of the divergence of rho times u dv. Okay? And that gets a minus sign on the right-hand side. So if we bring the right-hand side into the left-hand side, and we use these two results, so the minus sign on the right becomes plus on the left, and put them all under one volume integral, we get the volume integral of d rho dt plus del dot rho u dv equals 0. Okay? So our continuity equation, dm dt equals minus the mass flux, becomes a single volume integral, the volume integral of d rho dt plus del dot rho u dv equals 0 by way of the divergence theorem. Okay, this is true for any test volume. The test volume can be anywhere in the fluid flow. It can be any shape, any size. The only way this is true for all volumes V is if the integrand equals 0. So that gives us the usual form of the divergence theorem, which is d rho dt plus del dot rho u equals 0. Okay. Standard form for a divergence theorem, for a continuity equation, the standard form of the continuity equation. There's a special case that's called an incompressible fluid. So for an incompressible fluid, we have the density is a constant. Okay? So a typical fluid, such as a liquid, is very hard to compress it. If you can't compress it, you can't change the density. So typically for a liquid, the density is a constant. A gas is easier to compress. You have these tanks of compressed air. You can compress a gas. So for a gas, sometimes this condition doesn't hold. But if rho equals constant, d rho dt is 0 then, and rho can be pulled out of the divergence. So then we get the incompressibility condition will be del dot u equals 0. Okay? Del dot u equals 0. Physically, what that means is that if you have some volume, whatever flows into the volume has to flow out. Okay, we'll see that's the meaning of del dot u equals 0. There are no sources or sinks of fluid, and fluid cannot get compressed inside of that volume. Okay? So let me recap. In this lecture, I derived the continuity equation for a fluid. The reason I'm doing it here is because the derivation converts this mass flux integral using the divergence theorem into this divergence of rho u dv integral. And by doing that, we can combine both the left-hand side and the right-hand side and end up with this partial differential equation that's called the continuity equation for fluid flow. If the density is a constant, it reduces to del dot u equals 0, or u has 0 divergence. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.